7.3. It's the same thing. Okay. What?
That makes sense. Why were you?
Okay, so when we know that we have equilibrium and we know that we are at constant rates, we can actually find the equilibrium constant for that. We had rate constants with kinetics, so we also have equilibrium constants with equilibrium. So this is developed based on experiments only. So we're going to see a lot of tables this chapter with experimental data. The law of mass action was postulated by Cato Maximilian Goldberg and Peter Wage. I don't know how to say those names, but they gave a general principle of the equilibrium condition where if you have this reaction, so notice that the J, K, L, and M are the coefficients, that the law of mass action, or the K, stands for the equilibrium constant, is equal to the products raised to their coefficient powers over the reactants raised to their coefficient powers. Okay, and remember, we've seen brackets before. Brackets stand for concentration, which will most of the time be moles per liter, but this is just a general rule on how you would be able to figure out the expression for the equilibrium constant. So if I ever say determine the expression, I'm talking about this right here. But you would plug in what your reactants and products are, and you would plug in their coefficients as they are. Okay? Everybody makes sense now? Okay. We have something called a reaction quotient, where sometimes we don't know if it's at equilibrium or not. So we will find the reaction quotient to plug in information, and usually we use initial conditions for the reaction quotient. But when the way that we're going to know right now, if and so when you solve for it, it looks the same way, where products over reactants raised to the powers from the balanced chemical equation. But the way that we're going to know for now that we're at equilibrium is that if you were to solve it and the Q is equal to the K, then you would have the answer. And we won't really know that they're equal until 7.4 when we actually plug in numbers. But maybe you're going to be given two sets of information for a reaction, and you'll have to solve for Q, and it will say at equilibrium these are all the conditions, and then you solve for both of them, and if the answers are both equal to each other, then that's how you're going to know it's equilibrium. Okay? But so you just need to know that Q is equal to K at equilibrium. And we'll talk about when it's not equal to K later on. Okay? So we have this equation that we want to write the expression for. And so it's products over reactants, right? So we're going to have the concentration of NO2 to the fourth power times water to the sixth power. So those are both the products, and they go on top, over the concentration of ammonia to the fourth power times oxygen gas to the fourth power, or to the seventh power. Sorry, seventh power. So that would be a general way on how to set up an equilibrium expression. I'm waiting. Tops are products. Tops are products. Did I write it down? No. Okay. I could have. It's totally wrong. Okay, so now we have plugged in the brackets, right? So if from here, let's say we don't, because this is step 7.4, but if we are given actual concentrations for all four of these, we would plug in their numbers and actually solve for a value of K. It's 7.3, so we're not doing that today. I don't know why, but that's what it is. Okay, so now you just assumed, because I told you to do it, everything in here are gases, okay? So anytime you have a gas, you do want to plug it in. But that type of reaction is called a homogeneous equilibria because all of the reactants and products are all the same state of matter, okay? They're all in the same phase, state of matter, phase, same thing. But sometimes, often, we have heterogeneous equilibria, meaning that they're not all going to be gases. So if they're not all the same, for example, if we have calcium carbonate solid breaking down into calcium oxide and carbon dioxide gas, anything that doesn't change in concentration does not get included. And so what we know doesn't change in concentration are solids and liquids. So for this reason, we don't include solids and liquids into our expression. Sorry, did I go too fast? Ooh, I went. It's still going. Sorry. There you go. Okay.
Because it just cannot change.
Cannot change, yeah. So the solids and liquids cannot change their concentrations. And for this reason, we don't include them. So we only would include, and I have a picture. Let me move forward. So this picture, I took it honestly. But this is that reaction that we have where we have the calcium carbonate and we have the calcium oxide and the carbon dioxide gas. Well, if you notice, like, they're not changing from their piles. So they don't have any effect on the concentration of equilibrium. And so the only things that you would include for an expression when it's a heterogeneous equilibria equation is aqueous solutions and gases, because both of those could be changed. Okay? So that is a trick for some people where they may not, they forget about that, and so then they plug in everything when they really shouldn't. So for this example, let's write the expression for when we have solid phosphorus pentachloride decomposing into liquid phosphorus trichloride and chlorine gas. So what's the formula for phosphorus pentachloride? PCl5. And that's a solid. And that is, we're going to say that it's equilibrium, so we'll use the equilibrium arrow. So we show that forward and backwards reaction. And that will change to phosphorus trichloride, tri stands for 3, liquid, and chlorine gas. So Cl2. Yes. And it's already balanced, right? Yes. Awesome. Okay, so what should we not include from this reaction? Everything but the Cl2. So if it helps you and you want to cross them out, you can cross off all your solids and liquids if that is helpful to you.
Wait, all the liquids too?
Yeah, liquids and solids both don't get included. Only gases and aqueous.
I misunderstood that. I thought it was the other way.
Oh.
I thought it was like gases and liquids or something.
So the only thing we have to include is the Cl2, and it is a product, so it's just going to be the concentration of Cl2 raised to the first power, because it's an already balanced equation. And that's it. Okay? Now, if you are crossing things off, this is going to also be a trick. What if we had the reverse reaction? Like, let's say that it was the Cl2 gas with the PCl3 liquid, and then we had the PCl5 solid. If we had this reaction that we needed to write the expression for, and we crossed off these guys, the Cl2 is a reactant, so it technically needs to go on the bottom. So it would be 1 over for that situation. It would be 1 over the concentration. So you have to pay attention, is it a reactant or is it a product, and put it in the numerator or denominator correctly. And if there's nothing else to be put in the other side of the fraction, then just put a 1. Okay? Last but not least, we can also do this with pressures. It's the same process, but we would just use partial pressures. So maybe instead of giving you molarity information, I might give you ATM information instead. Same process where you do products of reactants, use the coefficients as the exponents, and that's it, okay? So let's just practice that using P's instead of brackets. for the reaction of the solid blue copper 2 sulfate pentahydrate heated to drive off water vapor to form the white solid. Sorry, I was very confused for a second. The wording on this. My apologies. Okay, so in case you probably have seen it before, you just don't know. Copper 2 sulfate, what's that? CuSO4. And then anytime that you have a hydrate, what you do is you put a dot, and then when it's pentahydrate, that means that there are 5 waters. So the CuSO4 5H2O is all of the copper 2 sulfate pentahydrate. Okay? So if you ever see that, that's what that means. And that's heated to drive off water vapor. So we have H2O, liquid, gas. Gases are vapors, sorry. And then white solid copper 2 sulfate. And then since it doesn't have any hydrates on it, that means that's the anhydrous. So that would just be CuSO4, solid. Okay? But we still want to make sure that the waters are balanced. So we would have to put a 5 for coefficient in front of the water. Okay? And then we do not include solids still, so we don't need those, we don't need those. So the only thing that we should have, and this is for the partial pressures, so we don't want to put brackets this time, we want to put a P for pressure, and we would say the pressure of H2O raised to the 5th power, because that's a coefficient of 5. And it's on the product side, so it's on top, and not the answer is. Okay, so today we just wanted to learn about equilibrium and then learn how to set up these expressions.